So I'm going to actually talk about a few broad things, but we keep talking about batteries and collective charging. We could have potentially benefited from collective organization in this session because I'm going to repeat a lot of what other people have said, but yeah, so it's been individual effort so far. Um, I think slides are coming up any moment. There we go. So I'm at Monash University. I'm also at Transport for New South Wales. At Transport, I am working to understand whether quantum technologies like quantum computers will have any impact. I've been accused of being a bit too critical of quantum technologies, so I'm going to try to further that reputation and be critical here. I don't work so much on quantum energy at the moment, but it's not unrelated. What I'm really interested in right now is quantum control to make quantum computers better. So here's some data where we've significantly improved the performance of some quantum hardware by applying optimal control. And I won't go into those details, but also interested in things like quantum chaos and foundations of quantum systems. But yeah, so it was about 10 years ago. We were at Benasque in Spain, and we were wondering what is the fundamental difference between quantum thermodynamics and thermodynamics. And I'm going to try to answer what I think is quantum thermodynamics later in this talk. And I think it's sort of still unclear. I was at a quantum thermodynamics conference a few weeks ago, and I think we were, as a collective, struggling to understand what quantum thermodynamics actually is. And I think there are more than one answer. And one of the things that we came across was thinking about how does time behave differently in quantum theory than in classical theory when it comes to energy. So work is effectively the same idea, both quantum and classically, but power is not, right? And this is sort of where these ideas of batteries arose. And they were really geared towards understanding some fundamental structures of quantum mechanics, not necessarily, as Francesco said, that it's not meant to be an advocation for a technology, but rather just understand how quantum physics is different. And so this is work with Felix, who spoke earlier or maybe yesterday. And the idea was to examine if we had a bunch of spins in some low energy state, if you were to raise them to a high energy state, how are different ways you can do it? If you do them individually versus collectively, is there a difference? And so collectively is labeled by this hash, and individually is by parallel lines. And then the difference in power, or the ratio of the two powers, is then the inverse ratio of the times it would take. And this was the idea. And in the worst case, let me go back there. In the worst case, or in the best case, you might expect that the advantage in power to be extensive. And in fact, that turns out to be the case. So then, is there something you can do with that? Turns out that you can't. And that's because when you put in the details of physical Hamiltonians and details of how matter really interacts and structure of Hamiltonian, you wind up with a bound that looks like that. So imagine this is your quantum advantage, like so how much more can you get? And it goes as some quantity that let's call k squared, and k is the number of particles that are interacting with each other. And that's usually 2 or 3, right? And 4 maybe. So it's not that many. There's also this other term that goes as m, and m is like if each particle is talking to every other particle. So if each of us are going to talk to every, if we're all talking to each other or screaming at each other, then m would be a very large number. But it's usually me talking to a few of you, or the speaker talking to a few people in the audience. So m can be large, but if m is large, then one can also explain that away in different ways. And I'll get to that in a second. So this advantage should tell you that like extensive charging power is unlikely in physical models. But that doesn't mean that you're not going to get some constant, some reasonable large constant charging power. And that's an open question. I wouldn't bet on it personally, but it's possible. Now, an interesting thing to think about here, and maybe this is slightly different than what others have talked about, is that we should compare this to how we get quadratic advantage in metrology. So in quantum metrology, you take n spins and you try to sense, I don't know, a magnetic field or something like that, and you get you get better precision that goes as that goes as 1 over n as opposed to 1 over square root of n in classical. Now, there are a couple of interesting things happens here. So it turns out that that quadratic advantage in metrology can always be obtained even for highly mixed states where there is no entanglement. And that similar feature is found in these charging power statements that were derived. However, the difference is that in metrology, it's the entanglement doing work. So if you have a large ket state or a G at Z state of n particles that is entangled, and each particle is experiencing the field locally, individually, then you still get this quadratic advantage. In battery, it's the opposite. It's not the entanglement that you care about, it's the collective interaction. So that collective nature is in the Hamiltonian, and that's much harder to get. Nature simply doesn't allow that. So the behavior is similar, but the quote-unquote power comes from somewhere else. Now, but then one might ask, well, what if we try to mimic something like metrology and set up a many-body system? So this is, again, the spins, and each of these spins are naturally talking to each other, and then you do local charging. So the interaction is internally there. And as several people have already pointed out, it doesn't help, right? So still no luck. Now, so was this all kind of pointless effort in the end? No, and in our own way, we were able to actually make some progress. So one of the things that we got out of it, well, the way we approached one of these studies was to look at the structure of something called quantum speed limit. So a quantum speed limit is really nothing all that different than a usual speed limit. So if you were to ask, like, how long would it take me to get to MCG for dinner? Well, MCG is about I don't know 1.5 kilometers, and can walk about a kilometer every 12 minutes. So it's going to take 15-20 minutes, right? So it's just the ratio of distance to time, distance to speed, and tells you the minimum time it's going to take you to get to MCG. But of course, we all know that some of us are going to stop at a bar first and get a couple of beers, and so it's going to really take an hour, right? So that speed limit is just giving you the minimum time, but of course you can do things along the way. Now, it turns out that speed limits were atrocious as they were defined previously, and they would give pretty bad answers. So for instance, imagine just a qubit, right? You start with this some state here on the surface of the Bloch sphere, and you try to move it to this state here, also on the Bloch sphere. Then it takes a certain amount of time to do that rotation. Now, it turns out that if you ask the same question for something inside the Bloch sphere that was not a pure state, so it's not on the surface, you get a much worse answer. It takes supposedly a significantly longer time. But actually, the amount of time for a rotation is the same whether you're on the surface of the Bloch sphere or inside the surface of the Bloch sphere. And this was recognized by Francesco, and he quickly came up with a couple of nicer quantum speed limits that were able to just outperform anything else that was out there, right? And it's just kind of an interesting mathematical curiosity, or maybe a computational tool. and so on, right? So this was one of the first results. It just works out really nicely, and it has such a nice interpretation. The first time I was introduced to quantum speed limit about 15 years ago, the person who introduced it to me said that quantum speed limits are genuinely quantum, and the reason is there's an H bar there. Which, for a theorist, that was very confusing because H bar is always equal to 1, so I don't know what you do with that. But this is actually not true. There is, in fact, classical speed limits. Obviously, you can't get to MCG very quick, instantaneously. It turns out that these things were quite loose, and we were able to tighten them. And this came straight out of the whole batteries stuff that we were working on. And then we started thinking about, can we even design better speed limits? So instead, never mind that I want to go from one state to another state. Suppose I want to ask the question, I've got a state with no entanglement, I want to get to a state with certain amount of entanglement. Then, wrong way. So you might ask the question, well, I want to, let's say this is a separable state, and this is this is a separable state, and this is an entangled state. You might go there via unitary trajectory. You might go there via some non-unitary trajectory using some ancillas. And it turns out that you can bound the time it would take you to generate entanglement or degrade entanglement, depending on what the environment that you're sitting in. And we can construct a speed limit. It turns out to be relatively easy, and they give you a much better estimate on how you build or degrade a given resource. So we came up with these quantum resource speed limits, and in particular, this Bloch sphere trajectory here shows how thermalization happens. This was again something that Francesco computed. And it seems a bit counterintuitive, but then you get a much better speed limit, because one might think that a thermalization, you might start from Bloch sphere, on surface of the Bloch sphere, go somewhere over here to a thermal state directly. Well, if you took a direct trajectory, you get there much faster, but that's not how a thermalization process actually occurs. So if you account for the correct geodesic, then you get a much better estimate for how long a process actually takes, how long it takes to deplete a resource. So again, theoretical curiosity and could be used as a tool. Now, again, I mentioned that quantum speed limits are not really quantum. So then this is maybe the surprising bit. A couple of years ago, speaking with Oscar Dalston, we were talking about quantum speed limits, and what Oscar realized very quickly was that you can use quantum speed limits to do a really interesting calculation, and that is how long, what are the trade-offs between energy cost, success rate, and time it takes to do a bit reset. Now, this is very closely related to a lot of the talks yesterday, where a major cost in computation is resetting the bits, and you don't want to take forever to reset a bit, because that slows down your computation. You want to do it fast, but doing it fast has a work penalty associated with it, and you might also get an error. So what you really want is a nice relationship between the work that you have to do in order to reset a bit and the error associated with that bit, which you can choose and you can bound that, and then the time it takes given some energetic resource. And this comes out, this super nice bound, and I think it's still one of the tightest bounds for this purpose, comes out straight from quantum speed limit. So we've taken this weird trajectory, maybe not the most optimal trajectory, but these are really interesting tools that lead to interesting results. So I'm going to wrap up here, and again I want to go back to thermodynamics, quantum thermodynamics, and what is quantum thermodynamics? And I don't really know the answer, and so maybe this is something we can argue about over lunch, or you guys can argue amongst yourselves. And then there are lots of different things that people study in this area. So for instance, the thing that I like to study in terms of chaos and so on is getting thermodynamics from quantum mechanics. I don't want to assume the postulates of statistical mechanics. I want to get thermodynamics out. And that's slightly different than extending thermodynamics with quantum features. So let's say you have a bath of spins and bath of fermions and bath of bosons or something like that. Or you might study time in quantum mechanics, and that was the original intention for going to batteries. And then on this side, we have more, this side we have more practical things like Landauer was the best way for us to reset a bit, and various other things that are going to be talked about later on today, like proof of work and what are the energetic costs of quantum computers, as Alexia talked about earlier today, and then energy capture conversion and so on, and that includes quantum batteries, which I don't know if I'm not convinced that there is there are technological results here or technological potential here, but maybe, right? Maybe it's worth pointing out that the bottom row here is about energetics and the top row here is about information. So that's another nice split here. And I think that captures everything, but there may be other things, so I'm happy to argue with you later. Thank you.
Questions?
Thank you for the nice talk. In the previous talks, we learned that you do not need entanglement for speed up for quantum batteries. And we also learned that in the decay model, there's a collective dynamics that results in extensive power. And it was all good. And there was also an experiment that shows that there's actually n-square power. It was all good until I saw the second or third slide that you showed where you say there's a theorem and there's like a nice quantum circuit representation of a physical system, and the theorem says that extensive power is not possible. How do you square the experimental results with the results of the theorem? Please correct me if I'm wrong. Maybe I'm missing something.
Well, I mean, you know, what they say about no-go theorems, they only prove one thing, lack of imagination. So, no, I don't know. I would say that so there is another explanation, which is there's a mean field explanation. So if you have, again, if all of us were talking to each other right now collectively, right, everyone's screaming at each other, that will be quite impactful, right? But and that could potentially give you more power. But there's a classical explanation to that, right? And I think this is something that probably other people are better qualified to talk about since they have done more detailed studies on that. So the theorem holds on its own, and we'd have to look at the experimental setup, and I'm sure we can close the gap.
So there's a contradiction to be resolved. Can we openly say?
I don't think so. I don't think there is a contradiction. I'm not troubled by it.
It's actually two different Hamiltonians. So in one case, there's a calculated system, and in another case, there is.
But just real quickly, maybe even Gianmarcello can add to that. But really, it's two different Hamiltonians. So in one case, it's just a collection of two-level systems, and there is no subdivision between what could be the cavity and what is the spins that are charged. So in the case of the decay model, where there was this super extensive advantage also without a strong entanglement growth, there is an effective n-body interaction that is mediated by the cavity on the spins. So that's how you get the extra scaling. I hope this answers the question. Well, for that system that Kavan was showing, then it's not possible. But for the system that Gianmarcello was talking about, it's a different system.
No, I don't think so. I mean, look, I'm happy to be proven wrong. You know, you can.
But I mean, yeah, it's fair.
Okay.
But that has been
I think there's a mean field explanation for it. Is the point that I'm trying to make.